Okay, so next topic is chemical reactions. Now, this is a big bummer for me because, again, chemical reactions is one of the topics like motion where we actually can do some cracks, you know. But alas, I'm sitting here in the prac room, and unfortunately, I don't think we'll be able to do any pracs in this topic. It's a bit crap, but you know, it's the same sort of thing with sport. You know, you just can't do pracs when you're doing things remotely. But you know, chemical reactions is still going to be the topic that we're going to look at now. Now, today's lesson is going to be a little bit more of an introductory kind of lesson, but it's still going to be something relevant to you guys. So I'm going to go with lesson 37, which I'm pretty sure we're up to lesson 37. Correct me if I'm wrong. I might be wrong, but that's what it looked like for me, is we're up to lesson 37, which is going to be, we're going to talk about identifying chemical reactions. And what I want to do in this lesson is we will be able to identify chemical reactions in experiments and conceptually. This is actually a bit of a weird learning goal, but the point is that I want you guys to be able to say, oh, that's a chemical reaction. I can tell that's a chemical reaction from, like, you know, because it's doing this, but also what does it mean for a chemical reaction to happen? If the whole topic is about chemical reactions, it makes sense to start off with, well, what is a chemical reaction and how do I know that it's happening? That's the main goal. So if you've got a second, can I get you to write down this section here? And then what we'll do is we'll move on. I'm going to do the same thing this term that I did last term. I'm going to throw these slides onto YouTube later on, but don't expect them anytime soon. It might take a little while for them to show up. So you should at least trying to get to class in time to take notes. The only reason I put them online afterwards is in case you guys struggle with bad internet, or I struggle with bad internet, then you've at least got the notes somewhere. So we're going to look at how to identify them. How do I identify them? What does it mean to be a chemical reaction? What are the different types of reaction? Now, some of this stuff you will have done last year. I was actually looking at my notes that I gave my year 9 students last year. We did do a whole term of chemical reactions in term 1. You guys might remember the antacid prac. You guys might remember you guys might remember what was it?
I remember the explosion one, the crazy one where, like, you know, all the teachers were at you.
Yeah, do you remember the one
Yeah,
where...
that was pretty sick.
Yeah, but I'm talking about last year. Do you guys remember doing one where you had a tablet that you put in something and then you filled up a balloon?
What?
No.
I don't remember doing that.
It's like that tablet thing, yeah, and then you check like the I don't know, I forgot the word, but like, you know, it's something to do with tablets. It's like a thing for your digestive system.
Yeah, antacid.
Yeah, antacid.
Oh,
that shit.
Yeah.
So that was sort of part of this one. There was another one that you guys should have done, which is the conservation of mass, which is you watch as if you make a gas and you put it on scales, it'd go, the thing would change, you know, it would go up, but the mass wouldn't change, and that sort of thing. So identifying chemical reactions is going to be our first topic in this. And to start off with, I thought I would show you this topic, this picture here, which won't make any sense unless I explain it. We've already done a topic this year called the periodic table. That's when I reacted sodium with water. And unfortunately, a lot of the coming style activities are what happens if we react sodium with water. And you guys now know it becomes catastrophic. So what we did was the periodic table, term 1, is we spent a lot of time talking about, this is a metal, this is a non-metal. We spent time talking about ions, and we talked about compounds. And so that's sort of realistically talking about the building blocks of, chemistry, and that's why I've got this picture here. It's just a bunch of blocks, whereas chemical reactions are more the changes in something. It's more like taking those building blocks and building something. That's what we're going to be doing this term. How do we build something new from a bunch of random blocks? What happens when we take those blocks apart? How does it work? That's what we're going to be looking at. So although we're going to be using a lot of the same terminology, we're going to be using a lot of the same concepts, we're essentially doing a different topic, because what we're not looking at, well, you know, we're not looking at how many electrons does fluorine have. We're looking at what happens when two nitrogen atoms come together. What reaction, what changes? So that's how these two things are different. Usually what you would do is, if we were doing chemistry as a whole topic, if we were doing year 11 chemistry, we'd do one thing and then the other. We wouldn't try and split it up. But yeah, this is going to be, so it's going to be a lot of the stuff related to the periodic table thing. So if you remember those notes, if you remember that information, if you do well on that test, then you should be okay for this. But we'll see how we go. This is some vocab. I thought I would start with this because it's a bit good sort of like activity, just to, this is something that I usually teach in year 9, but it's something that's usually, I think I may have taught this in periodic table, but it's something that I just thought, you know what, I'm going to go back over it again, because I know some people will have forgotten this. These are some vocabulary words that we use a lot. And we use these words all the time, so it's really good to actually know, how are they different? So an atom is one singular particle. Okay? It's one singular particle, it's one singular thing. You can have an atom of hydrogen, you can have an atom of carbon, you can have an atom of lithium. It's just one thing on its own. Okay? A molecule is two or more things joined together. Okay, so they're not atoms. Two or more atoms joined together. Now, the important thing with a molecule is they can be the same atom, or they can be different atoms. This doesn't matter if they're the same or different. If you've got more than one, then it's a molecule. A compound is when you have two or more different atoms joined together. So you can have molecular compounds. So for example, this is a compound because it's got two different types of atom joined together, a dark green and a lighter green. It's also still a molecule because it's still got two or more things joined together, but this is called a compound. You can have compounds that aren't necessarily molecules. They could be just a big structure, but we're not going to get into that really. I just want you guys to understand that they're a compound. This is when, if you remember CO2, so carbon dioxide, that was a compound, where H2O, that was also a compound because it's got hydrogen and oxygen. Even NaCl, that's also a compound, whereas a molecule would be, you could have hydrogen or nitrogen. You can have different ones too. You can have HCl, which is also going to be a compound, but it's also a molecule, so it can be both. An element is when you have one or more of the same atom joined together. Okay? So when I talk about an atom of, let's just say I'm talking about an atom of neon, or I'm talking about an atom of an element of neon, that's just one neon atom, that's it. If I talked about an element of oxygen, that's got two oxygens joined together, but it's just oxygen atoms. There's nothing else in there. It's only oxygen atoms. That means it's an element. So we're going to use these words a lot. I'm going to be using the word molecule and compound a lot. And I'm going to be transitioning between the two of them because essentially a molecule and a compound are almost the same thing. The only difference between a molecule and a compound is a compound has to have different elements in it. Whereas a molecule, it doesn't matter. So that's why I'll actually use molecule a lot. I'll use molecule to explain everything. But a molecule just means, oh, a couple of atoms joined together. And that's usually how atoms work. It's actually very rare that you'll end up with atoms by themselves. So this is something that you hopefully should have learned earlier, but this is the first time you're learning it, that's okay. Hopefully this explains the difference to them. It is annoying that some of these things can be more than one. As I said, an element can be an atom. You can have an atom of neon. That's, you know, that's an atom of an element. You can have a molecule of an element. You can have a compound molecule. You can have different mixtures of all these things. Now, what I'm going to get you guys to do now is let's talk about what does it mean to have a chemical reaction. In order to have a chemical reaction, you need to have one thing. You need to have a chemical change. Now, what is a chemical change and what other types of change are there? So a chemical change is, or a chemical reaction is when the bonds between atoms are broken and new ones are formed. Okay? So if I have two chemicals, if I have A bonded with A and I have B bonded with B, and then I break these bonds and make A bonded with B and A bonded with B, that is a chemical reaction because I have the bonds between atoms have been broken. I've broken the bonds between the two A's and I've formed new bonds between A and B. These are new. There were no bonds between A and B before, but now there are bonds between A and B. That's how you make a chemical reaction. At the end of a chemical reaction, you should have very different different compound. If you've got the same compound or the same molecule or the same elements as you did at the start, at the end, then you haven't actually done a chemical reaction. What you've likely done is a physical change. Now, a physical change is when the shape of a substance change, but its atoms stay the same. If you might want to think about this as you might have an A bonded with an A, and you might do all this crazy stuff, but at the end you still get an A bonded with an A. That is a physical change. It may look different, but it's still just a physical change. Physics meaning like with your like physical, like as in touching or something, whereas a chemical is like literally down to the atoms that are changed. So this is the difference between a chemical and a physical change. A lot of the time I'm going to be asking you guys, how do you know a chemical change has occurred? Well, if you don't know the difference between a physical change and a chemical change, then you can't possibly answer this question. I'm going to give you guys an extra little minute now just to copy this down. If you haven't copied it down already, you weren't aware that you were supposed to copy it down. You've got a little bit of time now, but I'm going to move on in a second. We all good? Can I move on? Can I get a guess?
Yeah.
Yeah.
Beautiful. All right, let's move on. So, physical change. What's an example of a physical change? Let's just say, and this is the original example almost. Let's just say I took a block of wood. Yeah, beautiful block of wood. Let's just say I chopped that down into smaller chunks of wood. Okay, good. Then I chopped those chunks of wood into sawdust. Okay, so it's really, really, really fine piece of wood. This is a physical change. Okay, And the reason this is a physical change is because it's still wood. I haven't actually made anything new. All I've done is I've just changed the shape. The other way that you can usually tell the difference between a physical change and a chemical change is if you could go backwards. Now, in theory, you can't go backwards in this, but if you had all the time and patience in the world, you could put each of these blocks like a jigsaw puzzle back together. And if you had enough time, you could actually take all this sawdust and put it back together to make these blocks of wood. If you had enough time. And when I'm talking about enough time, I'm talking about like millions of years. But I'm saying in theory, it's possible to go from one direction to another direction. Whereas a chemical change is a bit different. If I took that wood and then I burnt it, right? If I lit that wood on fire, that would be a chemical change. The reason for that is I'm actually changing the way the bonds exist. I'm changing from pieces of wood, I'm changing it into charcoal. I'm changing it into smoke. I'm changing it into dust, because what I'm doing is I'm burning it. I'm actually chemically changing the way those atoms are bonded to each other. So that's definitely the main difference between a physical and a chemical change. I also want to point out, by the way, get this, if you dissolve something, that's still a physical change. So if you take a spoonful of sugar and you dissolve that in water, that will create a solution. But that solution of water can be turned back into the sugar. That is actually a physical change. You're changing the shape. Now, you might not be able to think about, oh, but if you put sugar in water, how is it going to change the shape? What you're doing, what the water does to the sugar, is it actually breaks it down a very similar way to breaking down a piece of wood into sawdust. It just does it at the molecular scale. But it still is not a chemical. You're not making anything new. You're just changing the way that the sugar exists. So just keep that in mind, because I'm going to bring that up later on. So that's a physical versus a chemical change. So far, what have we talked about? We talked about atoms and molecules. We talked about chemical and physical change. So what is a chemical reaction then? A chemical reaction has a starting material and a final ending material. Now those things have special names. Does anyone remember what you call the starting materials in a chemical reaction?
The reactants.
Reactant.
Products or some shit? Is that?
Oh yeah,
What do
bro.
we call the stuff at the end?
Product.
Product?
Product.
Products.
Yeah, I guess.
And what's important here is that these are different. If they were the same, you wouldn't have a reaction. Products and reactants. Reactants and products. And this arrow at the top here is also how you can tell that a reaction occurs. So that's the starting point here. And in fact, all that stuff that I've talked about so far is stuff that you will have seen potentially back in year 9. If you don't remember it, take this as a bit of a refresher. So just getting those down here, the word terminology here, reactants and products. You can have lots of different products. You can have lots of different reactants. Okay, so you can, so there can be lots of different products. If you burn wood, there's actually lots of different things that you can get out of it. As I said, you can get gases, you can get liquid, you can get solid in the form of smoke, because you can get carbon dioxide. Believe it or not, when you burn wood, small amounts of water, liquid water actually comes out, but that liquid water then quickly turns into gas. So then you end up with little bits of steam. But yeah, you have to look at the chemical reaction. But I'm just going to move on now. I've talked about that for a little bit. Let's talk about this. So we've talked about chemical reactions. We've talked about, if you burn something that's a chemical reaction, you're changing the shape. You're changing, not the shape, you're changing the way that the atoms are bonded, okay? You're breaking the bonds in the reactants and you're forming new bonds in the products. So here's the question then, how can you tell that a chemical reaction has happened? Sometimes it's really, really obvious. And sometimes, it's not super duper obvious. So how can you tell? Well, there are 7 signs that a chemical reaction has occurred. And I'd like you to write these 7 signs down. You can paraphrase them, which means, well, you can take notes. You can shorten these words if you want. But I want you guys to write down these 7 ways that you can tell that a chemical reaction has happened. Now, usually more than one of these things will occur at the same time, but not always. Okay. Let's go through the first one. Gas bubbles appear. Okay, I don't know why appear is in capital. It shouldn't be, but that's fine. Gas bubbles appear. So whenever you see, how can I tell that that is a chemical reaction? Well, if there weren't any gas bubbles at the start, and then all of a sudden there are gas bubbles, that means you're making a gas. If you're making a gas, right, then that means there's been a chemical reaction. Now, obviously, I want to be specific here. If you heat up a jar of water, right, you will turn the water into a vapor, right? You will change its state, and that will make bubbles appear. But those bubbles are still water, so there hasn't actually been a chemical change. When I'm talking about a chemical change, gas bubbles appearing, I'm talking about, let's just say you add something and a bunch of carbon dioxide gets made, or a bunch of hydrogen gets made. Those are chemical reactions. So aside from making a gas, you could also instead make a solid. This occurs in something called a precipitation reaction, where it's going to be we're going to spend a whole double lesson talking about precipitation reactions very, very soon. But a precipitation reaction just means that you make a solid. You make formation of a solid. I can't think of any kind of precipitation reactions you guys would be familiar with. But yeah, when it's kind of always kind of cool when you take 2 liquids and you add them together and you get a random solid come out. The next one is a color change. Now, color changes happen a lot, and that might be, it might be when you're cooking sugar on the stove, and then the sugar goes brown because it turns into caramel. That is a chemical change. How can you tell? Because there is a color change. It's gone from clear or white sugar into a brown caramel. A lot of cooking is chemistry, by the way. Other ways you can tell color change, you could have 2 solutions that are colorless, go to make something pink. You could have something when you burn it, it goes from like a wood color to black. Well, that's obviously a color change, so that means a chemical reaction. Color change is a quick and easy way to tell that a chemical reaction is happening. temperature change is another one. Okay. You guys, last year, hopefully you guys did a fair bit of stuff about endothermic and exothermic reactions. That's reactions that produce heat or use up or absorb heat. They're your heat packs. Whenever you've got a heat pack that you're using to heat up your hands, that is actually a chemical reaction. Those little bags of sand, you know, that you hit, and I think it makes them warm. Those have actually got small, tiny pieces of, I think it's the tiny pieces of metal, the tiny pieces of pure iron, and they rust very, very
Black
quickly.
stuff.
Yeah, I'm pretty sure they rust really quickly, and that produces heat. I think that's how they work. It's kind of interesting. But if you add like a metal to acid, it will also heat up as it, you know, as it changes. You know, these temperature change is another easy way to check. Production of light. This doesn't happen very often. Actually, on the right here, I've got some glow sticks, but sometimes you'll see a chemical reaction will produce light. It might produce light because it's being burnt. It might produce light because it's reacting chemically. Keep an eye out. Volume change. That means you might end up with a bigger substance or a small substance. Like you might be like, hey, this only took up, you know, inside the test tube, and now it's exploding out, you know. And the last is a change in smell or taste. Now, of course, I'm going to quickly warn you guys, you should never taste anything in a chemical laboratory at school. But in theory, yeah, it's when if you've got a change in taste, then that means a chemical reaction is going on. Again, we go back to cooking. If you have got sugar and you heat that sugar up and you turn it into caramel, the caramel is going to taste different to what the sugar tasted because it's undergone a chemical reaction. And you can, you know, you can think about like cookie dough, how it tastes different to a baked cookie. And that's because it's undergone a chemical reaction. The taste and smell is different. These are the 7 signs of chemical reaction. Do you guys need any longer to copy these down?
No.
No,
We're done.
we're all done. Okay. So these are the 7 steps, these 7 checks. You don't have to memorize, well, you might sort of have to memorize them, but you at least have to know them. You at least have to know, oh, okay, if a question says, little Johnny reacted some hydrochloric acid with some sodium hydroxide, and notice the temperature of the reaction rose. Has a chemical reaction? Say yes, there's a temperature change. That's sodium hydroxide plus hydrochloric acid is actually one of the rare ones that it's actually pretty rare because it has a color, it has a temperature change, but you don't actually see anything different. They just look like 2 clear liquids make a, you know, hot clear liquid. It's kind of interesting. That was the end of period 1. Let's keep going. Also, by the way, I forgot my charger, so if my laptop randomly dies, I will warn you. Hold on a sec. Yeah, I've got like 20%. We'll definitely see if if I randomly disappear, it's because my laptop's running out of charge. But I haven't got too much left to go through, so we'll keep going. And then I will give you guys the task that I want you to work on today. So there are 2 quick laws. These are laws as well that, again, I don't necessarily need to teach you, but I wanted to at least go back over. This is something from last year. There are 2 laws. Those are the conservation of mass law. The conservation, here we've got, by the way, a production of gas. That is one of our signs that a chemical reaction has happened. We've got a production of gas, and this is, I think, like, this is when you think you take bicarb soda and you react it with vinegar. And what they've done is they put some they put some detergent in there so that it bubbles up, and that's what you can see here. There are 2 laws for chemical reactions. The first is that the total mass is the conservation of mass. That means that the total mass before and after the reaction cannot change. Now, I love messing with students with this one. What we do is you say, oh, well, you know, if I have a piece of wood and it weighs 10 grams and I burn that piece of wood, suddenly it only weighs 2 grams. And I say, well, where did the 8 grams go? We've obviously broken the law of conservation of mass. Does anyone know where that 8 grams goes if I burn a piece of wood?
Isn't it like the acid or something?
It goes
Smoke.
into your system. You go high.
Doesn't it go into the air, sir?
It
Yeah,
does,
doesn't it go to the air?
does go into the air. So even though, like, sure, it looks like, oh, it's all gone, but it's not. Like, it's turned into smoke. It's turned into carbon dioxide. Yeah, sure, maybe you inhaled some of that smoke. But the point is that it is no longer in the wood, but it's still present. What you would do is, if you wanted to double check that, you would weigh out the mass, and then you would put that in a jar. You would put that in a jar, and then you burn it in the jar. If you burn it in the jar, then there's nowhere for the gas to go. That's actually why the experiment that we usually do for this one in Year 9 is we actually get a flask. What we do is we put a balloon over the top of the flask, and the balloon over at the top of the flask, its job is to collect all of the gas. So as this here makes gas, in this case carbon dioxide, it gets collected at the top, and that makes the balloon bigger. But because it's sitting on scales, there's nowhere for the gas to go. Therefore, you measure no change in mass. Of course, that reaction never works, but you know, it's the theory. The second law is the law of constant proportion. Now, this one is the one that we don't talk about too often, but it's just, yeah. The idea is the total number of each atom can't change either. If you have 12 atoms of hydrogen in your reactant, if you count up all your reactants, you've got 12 atoms of hydrogen. At the end, you have to have 12 atoms of hydrogen. Now, they can be bonded differently, they can be in different places, whatever. Doesn't matter, but you can't just lose 2 atoms of hydrogen. You can't just lose 1 atom of oxygen. You have to have the same number of atoms at the start, at the end, and they need to be the same types too. It's a little bit different than the law of conservation of mass, but in my way, it's pretty much the same thing. I'm going to change this in a minute. If you haven't copied this down, if you don't have to copy it word for word, if you want to just take notes, that's okay, but we're going to move on in about a minute. All right, I'm moving on. Unless someone calls in and says, no, sir, I'm still writing it down. But at the moment, I'm just going to move on. Okay, so, okay, I've got 3 slides left. Let's look at this big thing here. This is a chemical reaction. Now, I could have chosen any chemical reaction. I chose this one because it's actually, you guys are in Year 10 now, and it actually means you can look at this. This is the classic vinegar reacting with bicarb soda. Okay? Now, you may not have seen this in this way, but yeah, this is still a chemical reaction. Let's break some parts of this down. Firstly, we've got our reactants. And then on this side, we've got products. Can you guys tell me, how many reactants do we have?
2.
2.
Mhm.
1, 2. How many products do we have?
3.
3. 1, 2, 3. Now, in a chemical reaction, we've got a couple of ways we can do these. We can write them down as worded chemical reactions, or we can write them down as, in this case, symbol-based. Whoa. Symbol-based chemical reactions. Okay, so we're word-based or symbol-based. In this case, this is symbols-based because we've got a bunch of symbols. Now, if we counted up each of the atoms on the left, they should equal each of the atoms on the right. Let's quickly do this for a couple of them. There is one atom of sodium here. Guess what? There is one atom of sodium here. If I was to calculate now, one of the harder ones is to calculate all of the oxygens. There is, where is it? I think I actually got this wrong, actually, to believe it or not. Because I'm just looking now, and it doesn't work. I think it's because this should be CO3. Because if I calculate all the oxygens, there should be 1, 2, 3, 4, 5. There are 5 oxygens here. And there are 1, 2, 3, 4, 5. There are 5 oxygens here. If I look at something like hydrogens, there is 1, 2, 3, 4 here. And there is, where is it? Oh man, sorry guys, I really apologize for this. I really ballsed up this this reaction here quite badly.
Yeah, because it doesn't look like it makes sense.
Yeah, exactly. Good. That means you're paying attention. If it doesn't make sense, then it means that it's not working. You're gonna have to fix this later on. But okay, let's just deal with the basics here. There are 2 ways we can do chemical reactions, words and symbols. There is a new thing here that I don't think I've ever really shown you guys. You guys don't think you've ever probably seen, which are these symbols down the bottom here. What do you think this G symbol here means? Take a guess.
Gas.
Gas. And you would be right. These down the bottom are actually called states. And you can have, obviously, the main states are solid. And when you have a solid, you write S. For a liquid, you write L. For a gas, you write G. For aqueous, what does aqueous mean? That means
Is that water?
Yeah.
Oh, okay.
Dissolved in water, which is going to be AQ. So before you copy this down, I want to show you. So on this page here, we've got aqueous, aqueous. So that means these two are dissolved in water. And the product is also dissolved in water. Now, water can't be dissolved in water because water is water, so it has to be a liquid. And carbon dioxide is a gas. Now, one part that this used to stress me the hell out when I was in year 10 was I was used to be like, how do I know if it's a liquid or a gas or what? The idea is most of the time it's going to be aqueous because a lot of our things are going to be in liquid, they're going to be aqueous, okay? Now, you should be aware though that stuff like carbon dioxide, hydrogen gas, helium gas, oxygen gas, these are all gases, so therefore they're probably going to be Gs. The only liquid that we deal with is water. And sometimes we will talk about solids being made, so I'll have an S for solid, but I'll let you know when a solid precipitate is solid is going to be formed. Now, I do have one more thing I want to explain to you, but here's the thing. What I'm going to do is I'm probably going to go through that in the last sort of maybe 5 minutes. What I'm going to do is I'm going to do this. I'm going to discard that, pause this. What I'm going to do is I'd like you guys to make a start on the, where is it? I'd like you guys to make a start on the very first activity on the style. So I've unlocked 3 activities. Review lesson chemical change. So this is the last slide I wanted to talk about because we're starting to talk about explosions in the third topic. I thought I would start to talk about that here. And then I'm going to talk more about this on Friday period 2, but I'll start talking about it here so you can at least answer the first couple of questions anyway. An explosion is, and like, there are a lot of different ways we can talk about explosions, but when you talk about an explosion, what is the basis of an explosion? So an explosion is a rapid formation of gas, okay? Now, that's all it is. But it's actually a really broad definition because it can be any gas. It can be nitrogen, it can be oxygen, you could actually make hydrogen, you could actually even make water vapor. You can have a water explosion, like a steam explosion is a rapid expansion of steam, and you can actually get steam explosions, and they can be very dangerous too. But any explosion is just a rapid formation or expansion of gas. This gas then expands quickly and pushes things. And that's what makes explosions either really good or really bad. I've got 2, and I'm going to do one more example at the bottom of explosions. The first one that I like is, I just pulled this one out because I thought, you know, I should show you one that's useful. And this is the sodium azide reaction. I actually had to look up the name azide, so don't think that I'm a super genius here. The sodium azide reaction, what it does is it's a really, really badly bonded nitrogen to 3 sodiums. You guys actually remember some of your stuff from term 1 with regards to ionic compounds, that this here as an ionic compound doesn't actually really make sense. That's true. It's a bit weird, and it doesn't make sense because it's so weakly bonded together. And what happens is that when you, I think, apply electricity through it, it quickly reacts to make sodium metal, which is, you know, but very, very small fragments of sodium metal, and a bunch of gas, a bunch of nitrogen gas. And that's actually what expands the airbag out. The airbag, when you crash into something, there is an explosion, and it just fills that with nitrogen very, very, very quickly. That's what it is. It's an explosion, fraction of a second. The second one is the potassium added to water. Now, this is very similar to the experiment that we did when we added sodium to water. Potassium added to water goes to make potassium hydroxide, but it also goes to make hydrogen gas. And this is the part that should be a G, sorry. This is the part here that makes it an explosion. And if you put too much of it in, that hydrogen will expand out really, really quickly, and that will cause a shock wave, which can shatter things and stuff like that. The reason I'm showing you this one is I'm trying to show you that the gas doesn't matter. It's still an explosion. The hydrogen can be even worse, because that hydrogen can also then react with oxygen to make water, which makes another, you know, reaction. And so you can actually get reactions upon reaction. The last one I wanted to show you would just probably be, sorry, yeah. I'm just trying to click on the, don't ask what's going on here. Oh, shit.
Wait, Mr. Gura?
Yeah.
Is it like, when like an airbag explodes and like it hits your face, doesn't it hurt?
I've heard that it's not that great. I've also heard that because it's literally an explosion, sometimes it can get really, really hot. So you got to be careful, but like, well, you're going to have to be careful. At that point in time, I don't care. Like if I'm involved in a car crash, having a slightly sore head because of an airbag is better than having a cracked skull because I've gone straight into the, you know, and in my opinion anyway. The last one I might show you is just going to be this one here. We're going to go with CH4 plus O2 goes to form H2O plus CO2. Now this is not balanced at all. I've got to give me a second to balance it. You guys are going to have to learn how to balance these on your own. For the moment, I will help you out. So that should be a 2 there, because there needs to be 4 hydrogens, and then that's going to be, that means that this one's going to have to be a 2 as well. This is going to be the burning of gas. Now, if you put a gas and you light it on fire, you can get an explosion. In this case, the burning of gas will make a, what it does, it actually makes gaseous water, but it also makes, actually, I think it makes gaseous water. It also makes gaseous CO2. And that explosion can be really dangerous. But it can also be really useful if you've got trying to drive your car and you're running your car off this burning of gas, then you want to be having a controlled explosion in your fuel tank. And that's what that gas does. It explodes and makes your, not your fuel tank, your engine, and that makes your engine go. So that's what an explosion is. It's a rapid formation of gas. We've actually got 4 different gases here, but in each of these, it's still an explosion. Notice as well that in most of these explosions, it actually produces heat. It doesn't have to produce hot gas. It can just produce gas, but usually hot gas expands more.